Hello, Namaste. I am Ramnath, who would like to present you the series on key learnings from chip development, part 5, which is on formal verification, particularly on equivalence checking. Formal verification is a method of verifying the correctness of a design using mathematical proofs. Formal verification is one of the smartest design bug finding methods, thus enabling a robust critical case system design. Hence, it saves costly embarrassments and enables quick customer wins. Formal verification analyzing methods discussed will be employing truth tables, binary decision diagram, and or combination circuit satisfiability methods. There are many updated versions of these, and I will give only the preliminary details on them. Thanks for learning along with me. Feel free to provide suitable suggestions. Thank you. Here we are again discussing at the stage when the data starts from specifications to architecture and further from RTL design, considering the IP design and the design constraints, how it is converted into synthesis, and then further how the synthesis design is converted into physical design, and then later to the tape out. Okay, there are so many steps in between, and here we are not mentioning those things specifically because the current situation doesn't demand. So as part of the RTL design, again as in the part 4 we have discussed more on these things. So there are many ways by which the design might not have been coded well. The processes aside to this, the processes which need to be taken care of, which may not be fully followed, and aside to that, the tools used to change the design at one level of abstraction to the next, and from here to the next, all these things may not be accurate enough, and their models may not be accurate, and sometimes those models also change from time to time to take care of other design complexities and all. So bugs in the design tools also may be there. Processes followed by the designers also will change. So various reasons, some of them will be discussed in the further sections. So due to that, you can observe that the bugs will start creeping into the system. So these need to be, they will be very costly when they at what stage they are actually found. So bugs found in the very early phase, the amount of money spent will be less, but as the situation design starts maturing, then the amount of money spent will be huge. Okay, so we need to know that the abstraction level higher it is easier and less costly to find the bugs and implement the bugs. Okay, but if the maturity, design maturity happens, then the amount of money spent and the level of complexity will also increase. And here, as we know, the RTL design verification will include two parts. One is formal verification and functional simulation based verification. And RTL validation includes these two. However, we will concentrate only now on the formal verification. Okay, in that we will be concentrating further only on the equivalence checking. Let us understand a bit more on where formal verification actually matter. Okay, so here the design and one abstract level has been translated into another form. So the RTL data has been translated into synthesizable netlist. Then it will be again translated into post-out netlist. Of course, pre-netlist, pre-out netlist, and all those things exist. But I'm directly taking from synthesized netlist is translated into post-out netlist, which is further translated into ECO netlist, engineering change order netlist, when there are any modifications need to be done. So there are variety of EDA tools which exist, which are shown here. Okay, so if you see here, the data needs to be equivalent between all these phases. Okay, so during this time, because data is transitioning from one form to another, there are many bugs start creeping in due to variety of reasons. Some of these reasons have been mentioned here for a specific case of an Intel Pentium processor based on 1994 study. Okay, so if you see again here, we will be wondering whether even though all these bugs have been cleared, were there any more bugs? That doubt we will have, because sometimes when we are working on critical care products, uh, any bug which may show up after 3 years or 5 years, that is also very damaging, either to the product or to the cost of the implementation, or to the credibility of the company. So we need to ensure that the bugs are removed in the beginning during the design phase. So if we go through again, so here we will know that these are all the different forms of the design. That means like design is in RTL form, another time it is in the synthesized netlist, another time it is in the post-routed netlist, and another in the ECO netlist. But if you see all these things, they are actually only, they say, you may see that RTL and synthesized netlist, they are actually dual objects. Okay, but if you really see, there is only one design. Okay, and these designs should exactly match, okay, to the specifications again, of course. So each of these pluralities which exist here, these items should be exactly same and one. So that is what I will just digress a bit. So this is called non-duality. Advaitam means like, Advaitam means like there is no dual, no Dvaya means in Sanskrit two. Okay, Advaitam means no two. So that will like RTL, synthesized netlist, there are no two items and there is only one. How will we say that there is only one item? That means like you need to bring in formal verification uh, tool to show as a knowledge. So this is the knowledge we are bringing in. Thus we are proving that RTL to synthesized netlist they are same, synthesized netlist to post-route netlist they are same. Like that the other two. So we are saying that by bringing in the formal verification tool knowledge, we are saying that these two items which are appearing to be two are actually one. So even in the Advaitam philosophy also, we will bring this knowledge to show that there are no two items, okay, and there is only one. So we are just giving different names to the objects. So here we are giving different names, like one point of time we are saying it is an RTL design, another time we are mentioning as post-route netlist. Like that we are giving different names, but this is all one design. If you can give it to the top level managers or respective technical lead, he will know that these are all different forms but of the same entity. So this is what actually, if we get this kind of knowledge in our day-to-day life also, we will really gain more traction. So when we are performing the actions, we have to know that whatever we are thinking, whatever we are talking, whatever we are doing, if they're all made same, then we will not have any stress. The major world religions each have followers who practice an inward path to know and experience their spirituality directly. A few of them are mentioned here. To ensure the correctness of the design, here we are taking only a small portion of the design which has a, say 6 inputs and 1 output. Okay, this is just to understand the basic concepts. So here verification means it can be either functional verification or formal verification. Okay, we'll understand a bit about functional verification as part of this. So verification means, have we made what we were trying to make? So does the product conform to the specifications? That is how the verification will proceed. So it focuses on functional correctness, verifying that SOC operates as intended and produces the anticipated outputs based on the input stimuli. So here it does not conform to the timing wise correctness. Okay, and that is not its intention also. So the formal verification got evolved, and here we will describe how these two slightly differ from one to another. So if you see functional verification, where it is a method of verifying the correctness of a design by simulating it. That means, like, here we will provide different vectors at the inputs, and we will give different stimuli, so that these internal states are depicted with dots or excited, and data flows from this point to further away to the output. So similarly, the data which is here will be moving from this location further away to output. So that is the that is why functional verification is called a dynamic simulation. And coming to the formal verification, it is a method of verifying the correctness of a design, same as before, but using mathematical models and equations. So that is why this is a static modeling, and here no stimuli will be used. Okay, and in the functional verification, it involves creating a test bench, because it is giving a stimuli and it needs to know which states it needs to excite and how to propagate it down, what all different stimuli need to be present. All that information need to be mentioned in the test bench and it needs to be crafted accordingly. However, in the case of formal verification, it involves creating a formal model of the design and then using mathematical reasoning to prove that the model satisfies its specifications. So we will come and discuss more on that aspect further. So we will just keep it aside here. And similarly, in functional verification cannot explore all possible states. Okay, and formal verification indeed verifies all possible states, because the way it operates is different to functional verification, because functional verification is from uh, top to bottom approach. That means, like, inputs to output approach. But in the case of formal verification, this data flows. That means, like, data is analyzed from output all the way up to inputs. That means, like, which all need to be set so that the output will be excited. Based on that, certain states will be selected. So these states to be excited, what type of inputs need to be selected, all these things will come into play, and that is why formal verification will be able to find more bugs than intended and than possible by the functional verification. And so this is what is the key difference between the functional verification and the formal verification. Yeah. So this there is also one more method in the formal verification. Also, there are two ways of doing. One is through equivalence checking, which is used mainly to figure out whether the post-routed netlist and the ECU netlist are same, or synthesized netlist and post-routed netlist are same. For that, usually the equivalence checking method is applied within the formal verification, and within the formal verification only property-based checking is used. This is mainly to ensure that specifications and RTL are correct and equivalent. Okay, so these are different ways of handling, and we will know more in detail. And if you see here, the if you see here, you will notice that, and all the states, all the connections have been removed, and you will notice that now these are the actual connections which will be seen through formal verification, highlighted in blue color. So it will go from bottom all the way up to the primary inputs. That's how the formal verification will go. The method of evaluating these mathematical equations and modeling will all happen in that way. Hence, it will be able to figure out all the possible ways by which the output excitation will happen. Okay, so if you observe here, there are, assume that in this case, so this state output depends upon the outputs of these two states. Okay, so and these ones, and this state output depends upon this input. Here again, this state output depends upon this state input. So if you see here, if you go through based on the functional simulations to excite this output, sorry, my mode it is going slow, fast. So if you want to excite this state, you need to just to excite the input like this, and then you will be able to move forward. So, but we need to understand that how all these different states, if they are not excited, will play a role, will not be exactly deciphered in the case of functional verification. Even though it is possible to miss out those states, because the way of functional verification happens is based on that, yeah, I know what to predict the answer. So based on that, it is created. Hence, there is a lot difference in the expected outcomes between functional verification and formal verification. If you see this uh, riddle, so if you want to know which of these cars or vehicles will reach the petrol pump, then usually each of the car has to be taken through the path, and then we need to check, and then we need to figure out whether they are going through the petrol pump or not. Okay, so is something like this. So each item should be taken through. But what FE will tool will do is like, it will start from the output. That means like which of the car will come here. So it will go according to this one, and then it will say that, yeah, this one here and here, like this, and maybe I got lost. So it will go through from the output. So petrol pump. This is how usually we will also do in certain solving the some puzzles. So this is the exact method by which checkers are written, and it will know which item is getting excited and all. So that is how the formal verification tool will be able to figure out the bugs in a times when formal functional simulation tools verification system cannot figure out. We will briefly discuss on the formal verification property based checking. Here the RTL is represented as DUT, and there are several states shown here with certain excitations. So this has some inputs and outputs. These inputs of the DUT are coming from another module. Okay, so this module can be part of the same design, and or this module can be coming from another chip. So here, that is why we will say that the inputs are internal variables of the DUT are constrained according to the design specification, and they could be assumed directives, because the inputs which are coming from this module, some of them we will not be knowing at the time of the design making. So we will be considering them as assumed to be true. Okay, and however, when we are considering the outputs, we know exactly like how the model should work. This information we will be knowing based on the specifications. So we will mention that the checkers outputs are the desired outputs, so they have to be true, always true. So the checkers are written either at the outputs or at the internal variables of the DUT. Okay, so internal cut points and all we can call. So they can be written using the assert directives. So when you find these constraints, checkers and RTL model, and when you give it to the formal tool, it will evaluate everything into mathematical equations, and then will decide whether the based on these inputs coming, whether the checkers will be true or not. So it will flag and ensure that the design is meeting to the specification or not. And since some assertive directives are added within the design or in the test bench, so what will happen is, like, whenever certain property variables as happen to be true, then those will be reported uh, to the outside world. So because of that, we will know what is the status of the situation of the certain DUT. So this is very important, because we don't need to wait till we are knowing through the outputs of this DUT. So we can figure out the internal state of the DUT very quickly as and when it happens. You can consider that this is more like the breaking news reporters. As soon as there are some uh, death due to some accident happening in even in some remote places, no, they will immediately report that, yeah, 3 people died due to car and motorcycle accident. So like that, they will be quickly telling. Is it really coming in the daily news briefs? No, most of them will not be coming as part of the headlines and all, but they will be reporting whatever happens within the DUT, whatever proper something which they find that, yeah, something may be important, they will be reporting all that information. So this is how the property checking can be carried out. And for this, the assertion language SVA or PSL are used. SVA stands here for System Verilog Assertive. This is part of the System Verilog language. And so we are clear now that assertions are properties which are primarily used to validate the behavior of the design. Thus, FE will trace the assertions back through the input and tell us what the input needs to be, so that it satisfies the assertion. To prepare this presentation, I have referred some of the following references. Please feel free to go through at your convenience. Thank you. And the next part will be presented soon on the formal verification.